I'd like to welcome everyone. My name is Rebecca Lowe. I'm the Adult Program Coordinator at the Lewis Public Library, and thank you for joining us this evening. And welcome to our series, Science and Society, Making Sense of the World Around Us. This lecture series is co-organized and moderated by Fred Dilla, Executive Director Emeritus of the American Institute of Physics and author of Scientific Journeys. Linda Dilla, former Public Information Officer at the Jefferson Laboratory in the U.S. Department of Energy, and Colin Norman, the former news editor at Science. So with that, I would like to turn this over to my colleague, Fred. So Fred, the floor is yours now.
Thank you, Rebecca. It's good to see everyone on Zoom for a very exciting lecture tonight. A few of you may know that we have a superb new telescope that became operational in Chile last year called the Vera Rubin Observatory. It's a remarkable telescope that you're going to hear about from the person who probably knows it best. Dr. Sandrine Thomas was the associate director for construction of this amazing device, and she's also in charge, associate director for the now operations of bringing the data to the world. Dr. Thomas has an amazing background. She did her undergraduate studies in Paris at the Institute of Optics, and she got her PhD from Nice by doing astronomy in Chile on the neighboring mountainside. So she is perfectly entailed to tell us about this wonderful new machine. The title of her talk is A Powerful Eye on the Changing Cosmos. So, Sandrine, I'm going to turn it over to you, and we're looking forward to the images you're going to show us.
Thank you very much, Fred, and thank you. So yes, I'm Sandrine Thomas, Associate Director for Rubin Summit Operation now, and it is really a pleasure and an honor to be here this evening to present the NSF/DOE Vera C Rubin Observatory, and now I will show some of the reason why we've built another telescope on Cerro Pachón in Chile and the status and what we're looking forward to. As Fred mentioned, I'm very familiar to that mountain, but I've been working for the Rubin Observatory for about 11 years now. I started only a few days after the first stone, which was the event where they actually started construction back in 2015. I did miss the event, but I was there a few days after. So let me jump in, if that lets me. Our mission is to produce an unprecedented astronomical data set for studies of the deep and dynamic universe, making the data widely accessible to the diverse community of scientists. And also, and that's the part I really enjoy, is engage the public to explore the universe with us. The NSF/DOE Vera C Rubin Observatory will really revolutionize the way we explore the cosmos by bringing the night sky to life. And you'll wonder why and how. The goal is to build what we call the Legacy Survey of Space and Time, the LSST, which is a survey that will last 10 years. And for 10 years, we will repetitively scan the entire southern sky using the largest digital camera in the world to really create a movie of the universe. And we call it the greatest cosmic movie ever made. And that started about 20 plus years ago in the mid-90s by two professors. One, Tony Johnson at UC Davis, really dreamt to have an all-sky survey to really explore the dark matter and the time domain. And for that, you need a very specific type of telescope. And so we had Roger Angel at University of Arizona from behind me, who actually had the knowledge to build such a large wide field telescope. And that telescope was actually called the Dark Matter Telescope. And the picture that you see here, if you see my cursor, is the first napkin drawing of what such a telescope would look like. It was literally on a napkin, and we took a picture of it. Someone kept the picture. It's a 8.4-meter telescope at that point, and had a 3-degree field of view. And I give you an idea of what 3-degree field of view is a little later. And then the years went by, and then in 2019, that telescope was renamed the Vera C Rubin Telescope in honor for the astronomer Vera Rubin. So you wonder, who was she? She was an astronomer who was studying galaxies, and she provided the first convincing evidence for dark matter by looking at how quickly the stars on the outside of a galaxy, distant galaxy, would move. And they found that the speed at which they moved was not in agreement with the models that we had. And the explanation needed to be that there was something else that we could not see. And that was one of the, as I said, the first convincing proof that dark matter existed. And she also was a strong advocate for women in astronomy. I must thank her for really pushing for women to have access to telescopes facilities. Otherwise, I wouldn't be here today to talk to you. So the Rubin Observatory is the first major US observatory named after a woman, and we're very proud of this. So we do emphasize the fact that it is not VRO, it is the Vera C Rubin Observatory. Where is it? This telescope is located in Chile. It's about halfway in the middle of the country. Chile is a very long, thin country. It is north of Santiago and in the region of Coquimbo. It's on a mountain called Cerro Pachón, and it is a jointly funded U.S. National Science Foundation, NSF, and U.S. Department of Energy Office of Science, DOE, facility. I mentioned earlier, our mission is to capture the cosmos and to build the greatest astronomical movie of all time. And you can see on this animation, the way we do that is by taking an image of the full southern sky in 3 to 4 nights only. And we repeat that over 10 years. So when you get at the end of the 10 years, per field or per part of the sky, we would have collected about 1,000 images. And those images, we use them in a way to detect very deep and faint objects, and also things that can move. And in order to do that, we need a very big camera, we call a wide field of view, meaning that we can capture a big part of the sky at once. And we need a telescope that goes extremely fast. So those were two big challenging on the technological aspect, in addition to being able to get a good handle on all the data that we're taking over the 10 years. Going back to bringing the night sky to life, Rubin will be a discovery machine. You can see that by taking repetitive images of the same part of the sky over 10 years, we can detect everything that's flashing, moving, or pulsating. So we have a model that we compare each frame to, and we can look at the difference and see what's difference in there. And that's really important for detecting asteroids and comets, pulsating stars, supernova explosion, hidden stars that we haven't seen before, completely new things, and rare things. So you can see that over the 10 years, we'll be able to really make we will unravel boundless mysteries and changes at all time scale. And when we say time scale, it can be something that happens as quickly as 3 to 4 nights, or on a longer term at over 10 years. Going a little bit deeper into the science areas, the Rubin Observatory was made to first to do dark matter and dark energy, but also we found that having the ability to capture the entire southern sky so quickly opened up the possibility for Milky Way structure information studies, solar system census, and as I mentioned a little bit earlier, the changing sky. Regarding the dark matter and dark energy, we've known that now for a while that we only can see 5% of the universe. 95% of the universe remains a mystery. We call it dark matter and dark energy because we cannot see it. The way we infer that it exists is by looking at the impact of those two things on what we can see, like galaxies and stars. So combining the ability of the observatory to detect very faint and distant objects, we really help the scientists to explore the nature of dark matter and dark energy. We will focus on supernova. We will focus on how the galaxies make clumps and clusters. We will focus on gravitational lensing to really understand better the nature of dark matter and dark energy. The gravitational lensing is interesting. It's like the dark matter really reacting like it was a lens. And that distorts the way you actually see the galaxy. So instead of having, for instance, a round spiral galaxy, we can see that the galaxy becomes a little bit elliptical. So looking at the direction of the ellipticity of that galaxy and other galaxies around, we can infer the presence and the location of dark matter, for instance. If we understand the distribution of galaxies, we can understand the cosmic web, and we can infer how the dark matter impacted the evolution of and then the formation of the galaxy, etc. And also, our current model of the universe do privilege galaxies of small sizes. And so really understanding and increasing the detection of galaxies, especially as we are looking far away, which means they're faint, will really help us understand if our models are right or not. So there's a lot to be uncovered using the Vera C Rubin Observatory. Getting a little bit closer to us, we will also make good discovery around our Milky Way structure. We will increase the map of the Milky Way by a factor 1,000 compared to previous survey that we have already now. And so we will be able to make a huge catalog of stellar population within our Milky Way to a level we haven't done before. With this data, we will be able to look at the distribution of colors and brightness of those billions of stars, and then hopefully understand a little better how our own galaxy forms, which gives some understanding of how other galaxies form. So for instance, one thing that I actually looking forward to read about is if our own galaxy is made of mergers of different galaxies, for instance. So if you look, if by any chance there was a bigger galaxy that not so long ago was coming towards or close to the Milky Way, it could be that that galaxy was slowly being incorporated or merged with our own Milky Way. And in order to understand that, we're looking at streams. So far, we have found 23 streams of stars, and those are literally streams around our galaxies. And so understanding how many there are, how big they are, how thin they are, can give us some information about galaxy growth and formation. So this is pretty exciting too. Getting even closer to us, solar system. Our own solar system has a lot of objects we haven't seen yet, and we expect to uncover 4 times more solar system objects than we actually currently know. When we talk about solar system object, it can be asteroids, it can be comets, it can be the unknown planet beyond Neptune. And so that's the different distances at which we're looking at the different potential objects. The ones in the asteroid belts, so between Mars and Jupiter, or in the Kuiper belt after Neptune. And as I mentioned, also the potential additional planets that we don't see yet. We can see, again, very faint objects because we're integrating their lights over the 10 years. And we also are very sensitive to anything that moves. And that's why we can see more than what we've seen before. The other important and part of this science case is that we will be able to detect near-Earth asteroids as well. So potentially dangerous asteroids that might come towards us. We know now most of the asteroids that are a kilometer in size, but we'll be able to detect about a factor 2 to 3 more of the 140 meter and plus, which still have quite a huge impact on Earth if we get hit by them. And so discovering them earlier help us act on their trajectory, for instance, or avoidance. Okay, so that's for the solar system. And then the changing sky. By the technique I explained earlier, and really looking at differences between all the hundreds of images that we're getting, we'll be able to detect about 10 million changes per night in the southern sky. So that's a lot of data. That's a lot of changes. And we will count on global follow-up to really look in more details of those that are really rare events. And so to do this, we actually have a community. So we're taking the data. We're the first step, really providing those differences into our images. But then we go through a community of brokers, we call them, which are software systems that process all those alerts, sort them, make sure that we're not using false detection. And then when they sort them, they really sort them by categories to help the scientists behind or the scientists after us to do their own research. That means that also the telescopes around the world that can see the same part of the sky will be listening. And if there is something like a supernova, for instance, that is happening, they will aim their telescopes to that particular part in the sky to do some deeper observation of that object. Supernovas can be as short as a few days, so you have to act very quickly when we discover one. And the LSST, the Rubin Observatory, is a telescope that has a high resolution for its field of view, but it doesn't have, for instance, the ability to have very fine study of the light coming from different wavelengths. And so you will need a different type of instrument called a spectrograph to do those type of follow-up. So it is really important to have that. And my next slide is about those different telescopes that will listen to those alerts. And those alerts are public too, meaning that if you do have a telescope in the right place, ready to look at the sky, you can actually subscribe to those alerts and then do your own follow-up as well. And we also have the same process in reverse, meaning that we can also stop our own telescope to direct the Rubin Observatory to a certain part of the sky. We call them target of opportunity, just in case another facility, such as LIGO or Virgo, which are looking for gravitational waves, if they discover something, we can actually follow up. So the alerts are going in both directions, although they are actually more of the time they go from us to the rest of the observatories than the other way. All right. And then, of course, with the amount of data that we're going to have and the cadence that we will have, we will be uncovering the unexpected. And then I cannot talk about those at this point because we don't yet know what we don't know. And that's what's exciting, really understanding new mysteries and then potentially changing theories and model with what we found and that are not predicted. All right. So that was a very quick overview of the science that we can do with the Vera C Observatory. And I really hope I can stand in the next year or two here and then show you what we have done with the survey. But before I do that, I will give you some insight on the technology behind it. Because as I really quickly mentioned at the beginning, it requires really cutting edge technology to take so many data so quickly. So we have, again, a huge camera. You can see the size of the camera in this picture. We have a fast telescope with a novel 3-mirror design. And then we have a global data management system that is required to handle terabytes and terabytes of data per night and lots of changes per night. The camera has 3,200 megapixels. This is about 67 iPhone. That's what we checked. And it would take 400 Ultra HD TV to display a single image. And you will have a little bit of a taste of that as I show you our first look images. They look tiny and you do want a big screen. I did mention the field of view earlier. You can put 45 moons in your field of view, meaning that for one picture that you take on sky, we can put 45 moons or 7 moons across. Most of the telescope can only fit a few moons. So it's an improvement compared to other telescope and also other survey telescope. And we have 6 filters. The filters are spanning the ultraviolet to the infrared wavelength. So looking at what we can see in the visible is just expanded it on each side a little bit. And this is a view of the focal plane. So this is a view of the detector from where the light will come into the camera. So you can see the little squares are the CCDs. They're 4,000 by 4,000 pixel CCDs. And we have 189 CCDs. And you can see them in full scale here. And you also have a raft, which is a 3 by 3 CCD little square. And so the first time we went on sky, way back when to do first steps, it was just this little camera, which actually turned out to be pretty spectacular already. So now we're blessed with a full detector. The Simony Survey Telescope so hosting the camera, is a very compact telescope. It's a 10 meter by 10 meter cube, and it has to move very, very quickly. It has to move 350 tons of steel in about 5 seconds. And then we change fields every about 40 seconds. And so hopefully that video will show without the sound. This is a test that we've done about 3 years ago of the actual mount. So it doesn't have any optics in it, but hopefully your network is quick enough to see how fast that telescope moves from one side to the other. It's about 10 degrees per second. So that means that if you want to do the 360 degrees, you need 36 seconds, which is extremely fast for such a telescope and 350 tons. And one aspect is that's also challenging and also remarkable is it's a point and shoot telescope, meaning that it moves in 5 seconds, in 3 seconds, and then has to stay steady. Everything has to be in place within 1 or 2 seconds, and then you repeat. So you don't have time to adjust, and then repoint your telescope to where you want to look at. It has to be going in one place, keeping all the optics in shape in a matter of a second or two. It is automated as a result. If you do move every 5 seconds and you take a 40-second exposure, you don't really have time to enter coordinates. So it is what we call the scheduler that does that. It's a software. It's the brain of the telescope, we call it. And it actually takes into account the status of our survey. So again, how many images we took per field, where we are in like 3 to 4 nights that we've done the entire southern sky yet. And so it will choose the part of the sky that haven't been looked at yet. It will look at potential clouds. We do have a camera that takes a picture, very low resolution picture of the full night sky to kind of detect where the clouds are. And that software is capable of looking away from that direction. We also avoid the moon. The moons are very bright. They would saturate our detector. So we have to move away from the moon. So all that is being taken into account to calculate where the best position of observation is at each step. So every 40 seconds. We also have a interesting optical design. You can see on that animation, the outer surface of that mirror reflects the light coming from the star, then goes to the secondary, the tertiary, and then the camera. I play it again. And you can see on this picture that we have 2 different mirrors made of a single glass, which is the first of its kind. It was probably complicated to fabricate, but I got it as I joined, so it was already made. And for me, it was really good because that allowed me to have the primary and the tertiary in perfect alignment all the time. And this is really important because, just take one. Because as you're moving quickly across the sky, you can see how the alignment of the optics can move a little bit. The primary mirror is about 16,000 kilograms, and it will bend on its own gravity as you move lower in elevation. So you will distort that mirror. And you can see right here our primary secondary mirror. Same for our secondary mirror. And then the optics, so the camera and the M2 also are top heavy over here a little bit. So they will actually distort the telescope ever so slightly that will distort, and the consequence is that you will have a worse image quality. So your image is going to become blurry. So in order to compensate for that, we have a sophisticated way to control the shape of the surface and the position of the optics using what we call an active optic system. And behind the mirrors, we have a set of actuators. We have the set of little pieces of actuators that push the mirror in very locally that will enable to compensate for instance, the distortion due to gravity. So you keep perfect shape for the optics, which means that you keep a perfect image at the end. And then we also have the same on the M2, you can see up there, which is our secondary mirror. And we have also hexapods, which are the same type of bigger actuators that will allow to keep the position of the camera and the M2 relative to our M1. So all that also requires a lot of computing and understanding of how they distort and then send the correction to the mirrors. We have 156 actuators on M1, M3. We have 72 actuators on M2, and we have 2 hexapods. And then finally, the telescope has to be able to detect very faint objects. And to do that, we don't want to lose any light coming from the stars. So that means we have to have high reflectivities of those mirrors and very good transmissions of the optics. And I'm going to let you watch this. Our mirror has different layers of coating to allow to enhance that reflectivity, and that's the spot. Here it is. So you are inside what we call the coating chamber, and we have those big pieces that have the lights in it. They're called magnetrons, and they deposit different chemicals on the mirror. And the last one is silver. So we are depositing a layer of silver, very thin layer of silver that will be reflective, and then some protective chemicals as well. I like this video. It just gives me goosebumps every time. So our primary tertiary mirror was actually coated in 24, and our M2 was coating in 19. And you can see this is actually one of the other curves I show, but this is the percentage of reflectivity that you get per wavelength. So depending on the light, the color of the light. And then you see that it's above 90%. Our requirement is about that much. So we're really happy with the amount of light we can get from the stars. This is a picture of our coated M1, M3, and you can very see clearly the M1 surface and then the change of curvature for the M3. And this is our big coating chamber. So you were looking at the inside of that earlier. And this is just a picture of me taking a selfie. I'm very lucky that I could take such a selfie. This is the M1, M3, and then I'm looking towards the M1, M3. And in the back, you have the camera. Anyway, it's complicated, but I just love that picture. So I thought I would show it. Okay, first photons. So back in 15th of April, 2025, we managed to have all those amazing equipment on the telescope all aligned, and we took our first images. And we actually were very happy. Not only because we took our first images, but it looked like that. So I explained. The top one is the 189 CCDs. So that's the full image, and it's hard to see anything. So I blew up a 3x3 region. So that's at the center right here. And you can see what we call donuts. You can see donuts because of the hole in the center, and it's a big ring. And that told us that we were actually really close to having our optics aligned. and we were just a little bit out of focus, like 1 millimeter out of focus. So when you think about how big this telescope is and how big those mirror is, and the fact that we were off just by 1 millimeter was really exciting. And it took us 3 images to get into focus. This is a raw image, so maybe not the prettiest, but that was our first raw image. Now with that, a few months later, that's what we managed to create. So this is what we call the cosmic treasures chest. It is focused on the southern region of the Virgo cluster, and the full image here is about 25 square degrees. So it's about 1.4 times the size of the camera field of view. Remember where you had 7 moons. So it's a little bigger than that. And it was taken in 4 different colors. And we took about 1,180 images for that image. So that means that we not only need a very sophisticated telescope and camera, but we also need to have the infrastructure behind it to take those thousands of images in different filters and then collapse them to create such a beautiful image. And you can see, I don't know how big of monitor you have, but you don't really see much on this image. I mean, you see like pretty galaxies, but if you go just a little bit deeper and you zoom in, that little region, you can still see a lot of more details. You can see a lot of galaxies. That image actually has about 10 billion galaxies in it. And so that has a little less, but you can see all the structure and the gas and the dust that surround some of those galaxies. And this is one of my favorite. This is a background of a lot of people in our project, where you have different galaxies and they don't really seem to interact with each other. But right here, you can see that the dust from the different galaxies start to interacting with each other. And this is, dust and stars and things like that. So you can picture what I've mentioned at the beginning, where who knows what will happen in the next millions of years, but those might actually be becoming just one galaxy. Who knows? All right, and this is, again, to put things in perspective, this is only one tiny part of the focal plane. This is another of our first look image that we showed last June. This is the Trifid and Lagon Nebula. It has 678 exposures. And that was actually taken in only 7 hours. And I forgot to mention the one before was only 10 hours over 7 nights, which is incredible. There's no other facility that actually can take such a big image and such a depth. So seeing very faint objects so quickly. It would take either telescope 10 or 100 years to get such an image. So that's really the power of the Vera C Rubin Observatory. And you can see here a link if you're interested. There's a lot more in that link. All right, and then my favorite movie, time domain, so changing sky. Maybe I shut down that. Discovery of asteroids and comets. So this was also taken during our campaign for the first look event, and we were looking at anything that would change in the sky. And you see, we made not only 1, 2, not like 50, but on the first night, we almost discovered 1,000 moving objects. And then after a few nights, 7, we had discovered over 2,000 asteroids, which is incredible. And this was only over 7 years old. So that was only a tiny portion of the discoveries we have yet to make. And so with those and then repeating observation, we'll be able to not only detect them, but also understand their trajectory and their brightness. So this is really, really exciting. And we also managed to take a peek of a new comet that was discovered last year. We did not make the discovery necessarily, but when we actually heard about it, we went back to the data and then we had it in our data. So that also shows the power of really digging through the amount of data we will have and then discovering new objects. All right, and pushing data boundary, as I mentioned, we have a lot of data. So what do we do with it? How do we deal with it is going to be extremely important. And when you think about it, when you think about in the 90s, when that telescope was being thought about, we were ordering DVDs by mail. We did not have the infrastructure to handle that much data. But now we do. We have the storage capacity and the computing power. We have the network bandwidth, and we have very sophisticated algorithm. And I know a lot of people hear about AI. This is something that we use a little bit, but we also have very other type of algorithm that allows us to do what we do. The journey of the data starts on Cerro Pachón, where the data is taken, and then goes through fiber links to the US in California, where the National Accelerator Laboratory is, SLAC, and that's where we have all the data being stored and processed. We process about 10 million of alerts per night. And then we also do annual data processing. And then the data will also go to a French data facility and UK data facility for processing and also access for different other countries. And that's about 80 hours after it's taken. There's a lot of really high number of these slides. They don't all mean a lot to me. So I will try to at least explain a few. We're getting in 1 year more optical and infrared pixels collected than all previous combined. We have 20 terabytes of data every night. And after 10 years, we will have more than everything that has been written. And that's looking at the Library of Congress, which is the largest library in the world. And we see that their storage is going to be less than how much we're going to get after 10 years. And more people will have access to those data than ever before. The US scientists and Chilean scientists will have access to the SLAC data computers. They will need only a laptop and a connection to be able to connect to our science platform and to be able to do their own research. So the data will be stored in that data center, and the codes will be stored there, and the computing capability will be also at the SLAC, so then people can actually connect. So they don't need sophisticated computing capability to do those the science that they want to do. And then the last point, I will go back to it, is the data will be for scientists, but it's also for everyone. We have very state-of-the-art algorithm to be able to do those discovery, either by having sophisticated way to do the differences when things change, or to sort through those billions of objects and make catalogs, and then find those rare events. And that's what that slide shows too. Remember the movie I showed at the beginning of the talk? The data system will need to take all those data collected, combine to emulate longer exposures. So you have to very, very carefully align all those images so then it can stack up properly. You don't want them to be a little shifted. And that's what we really enable to get good signal compared to the noise and potentially extract fainter objects. We will have annual data release, so calibrated images and catalog of billions of objects every year, and that includes their position, their shape, and then how bright they are. And we have 11 annual releases in total. And here's my slide on data for everyone everywhere. The data is accessible to most people. As I mentioned, all the US and Chilean scientists, also scientists across the world that participate to some of our in-kind contribution by either doing some technical work or writing algorithm to help us. And then after 2 years, it's going to be more public for scientists. It is also available for volunteers around the world. And we are using a platform called Universe to do citizen science. So this is really the first time this much astronomical data will be available to so many people. And that's because our Rubin Education and Public Outreach program was built as we were building the observatory. It was not an afterthought. It was in the proposal since 2014-15 when the project started. And as a result, we have a very sophisticated program that focuses on 3 main aspects: the formal education, the public outreach, and the citizen science. So formal education, we've worked with teachers from grade 8 all the way to beginning of college to deliver free online classroom-ready material for students, but also for teachers. We're not expecting every teacher is an astronomer, so we were making sure that all the material, all the codes was actually ready to use. And the best part about it, that I think, is that they're going to be using real data. So our education program has worked really closely with our data management program to be able to use the same codes and the same data. So this is really exciting for students. They can really be astronomers. Public outreach, we have put a lot of effort into our websites and visuals and videos, and a lot of our product is mobile friendly, so you can use it on your phone. The one thing I would encourage you to go to also is a program called Voices on our website, and it's really to highlight all the different people that have contributed to the observatory. And I'm not talking only about astronomers or scientists or engineers, but also bus drivers, mechanics, cooks. It takes a lot of different people to make an observatory work. And that's where we try to also communicate through the voices. So then people who are very excited about the universe and the sky can be part of that. And then finally, the citizen science, which is an opportunity to do research using the Zooniverse interface and really look at real data, such as comets. So we have 2 programs right now called Comet Catcher and then Rubin Difference Detective. And there, for everyone to help the observatory go through the tons of data we have to spot comets, for instance, or to make sure that what we're seeing as alerts are actually astrophysical events and not imposters. So if you're interested, this is the link, and there's more projects coming up. And then also we have an interactive data exploration with our Orbit Viewer and Sky Viewer. The Sky Viewer in particular, if you want to dive in that image that I showed earlier and see how far deep you can go, this is really impressive. I think my kid played nonstop for about a week, really looking at all the different objects and all the different galaxies. So that's also available on our website. And then that's it, I think. I'm going to leave you with a quote from Vera C Rubin. Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies. And a few other links. But I think that actually summarizes some of the goal of Rubin. And just one more picture for fun. Okay.
A beautiful picture to end with, Sandrine, your talk, not to end our session tonight. I knew we would not have to worry about questions on such a wonderful talk. And let me first say that since Sandrine gave such a wonderful talk with a lot of information, many of you will want to watch it again and study it. It will be put up on the Lewis Library's YouTube channel in a week or two. And you can just check back there to watch it again. And also note the Vera Rubin Observatory website. The last 5 or 6 slides that Sandrine showed you how much was there for the ordinary person to look at, especially if you want to become an amateur astronomer yourself. So with that, we'll try to get a few of the questions in before our time is up. And let me start with one of our regular viewers, Anne Finkbeiner, and she asked the question I would have asked you first. So you've been operational less than a year. In your mind, what's the most interesting observation that the telescope has made so far? You probably have a long list, but pick one out.
So first, a little bit of a correction. So we have been continuing some of the tweak for the telescope. So we've been in early operation, which means that we haven't yet started the actual survey. So we haven't yet started to collect a lot of those data that will actually go towards those science case that I explained. That being said, I think you've seen those asteroids. I think that's to me, the most exciting part of those discoveries is like to see everything that's changing and how many we will detect in very little time. I think that's pretty much what's been the most exciting so far.
So you very eloquently described how this was the vision of Vera Rubin, who was first to point out the existence of dark matter. One of my colleagues, Jim Strachan from Princeton, is asking, there must be dark matter near us, say between the Earth and the Sun. Is that too small a space for this telescope to detect the presence of dark matter?
At the solar system level, yes. However, looking at our own galaxy, that's the scale that will give us some answers to potentially where the dark matter is and how it impacts the formation of galaxies. So looking at where the stars are distributed and how those mergers happen will potentially give us some clue. But the solar system itself, yes, it's a little too small.
So I have an interesting question from another colleague, Philip Drouin, who used to work at the State Department, and he's wondering what is the relationship between the government of Chile and the U.S. agencies, NSF and DOE, and maybe other partners that got this telescope built.
Yeah, so it's been a long history. So you mentioned my PhD thesis that I did on another mountain. So I studied my undergrad at Tololo, and Tololo is Tololo has a 4-meter telescope called Blanco. And then other telescopes started to be built, so Gemini and Rubin. All that to say that Tololo, I think, was built in the 50s. So there's a long history of the US government and the Chilean government getting agreements, we call them MOUs, to enable the US to actually build telescope in Chile. So we do actually own the property of the mountains, or the US government. And that's a very tight connection. This is not the only telescope, or these are not the only telescopes. There's also some a little bit more north of La Serena, Las Campanas. And there's also some you might have heard in the north of Chile, but they're from Europe. They're actually collaborating with Europe. And they have a radio telescope and a few 8-meter telescope, and they're building a 39-meter telescope. And so there's a lot of telescope in Chile because that's where there is really dry air. It's very clear. It's usually on top of big mountains, which allow the moisture to be kept at the bottom. And it's also very, very dark, although we do have an increase of mining around that we have to deal with. So there's been activity for a long time and a very good connection with the Chilean government, the US government, and even Europe. We do have programs where we actually make sure that we collaborate with universities in Chile, either at a scientific level or engineering level. All of our staff, mostly in engineering, is from Chile, and they're amazing engineers. So yeah, that's
So there are a number of questions having to do with environmental aspects that might affect your imaging. You mentioned how you deal with clouds, but Chile is an earthquake region. How do you isolate this fantastic mechanical system from seismic vibrations, either modest ones or earthquakes?
Yeah, we do have a few earthquakes, and all of those telescopes are built with the pier, so the mounts mostly isolated from the telescope, and we have telescopes on dampers, so the telescope can move, or the pier can move, but the telescope will move a lot less when we have an earthquake. So that has been pretty much the design of all the telescope in Chile, from like the 1 meter to the 39-meter telescope, is to really make sure that the telescope itself is not connecting to the building itself. And so when there's an earthquake, the building moves, but the telescope is isolated from it and more on dampers.
One of your other environmental problems is the huge number of Earth satellites, which are affecting astronomical observations. Many in the audience have probably seen pictures of a modest telescope just staring at the sky for a few minutes, and you see all those satellites streaking across. How do you subtract that data from your observational data?
So there's different things we do relative in respect to satellites. So, and then I go to your specific question as a third option. So the first option is that we actually have been working with some of the companies to make sure that they use material that doesn't reflect the light from the sun as much. We often are sensitive to those satellites when the satellites for the network, right? So the one for internet, we are sensitive to those in the morning and in the evening, like at the beginning of the night and the end of the night. So we definitely do work with those companies to make sure that they don't reflect as much light. The way to think about it is we're very focused on either differences and or addition to all those data. So when we actually add on thousands of images, if you do have one satellite in the image, you can either remove that image if it's too bright, or you can cut out, at least in that portion of the image, you can cut that portion of image out, so then you don't actually add it to the stack. We have a way to remove them also with algorithm. So we know we have a streak that long is not expected. And so we actually remove that, especially if we don't see it in different other images. So we do have ways to remove them. And we also, especially with those network satellites, we can get from them the trajectory of the satellite, so then we can avoid. With the scheduler, remember the brain of the telescope, we can actually remove the area of the sky that has the brightest satellites coming in.
Another environmental question. You showed us how carefully the silver coatings were put on the mirrors and how important that they are, that the surface has to be very precise compared to optical wavelength and very clean. How do you clean those surfaces on the telescope if there happens to be some detritus that dropped on the mirror surface?
Yeah, that person might have gone to the telescope in the last few months. So we do have two different techniques. We do have a CO2 cleaning. So we do that once or twice a week. And so that's really to remove the dust that we have. As you mentioned, we're in a dusty environment. We haven't done it yet, but we have the plan to pave at least a road around the observatory to limit the dust that's coming into the dome. So CO2 cleaning is great for that. Now we have had, we haven't had, but we've seen at a telescope with bird poop. The birds are there, it's their habitat. So we do have to clean those. And we have in situ wash where we actually use soap, very soft sponges. And we do what we call an in situ wash, where we actually use water soap. We angle the telescope in such a way that the water flows and don't hurt electronics. And then we do that monthly. We haven't done it yet. We're still ironing out some of the techniques, but this is due. We need to do that soon.
Thank you. I had to ask that question. My wife, Linda, knows I spent my scientific life making clean surfaces, so I like to keep them that way. Our time is up. I want to remind people again, they can see this talk again, and going to the Rubin Observatory site, you will find the rich array of information that Sandrine has talked to us about. So I want to leave you with one other thought, that a month from today, we have our next talk will be by the former director of the National Hurricane Center here, Dan Riley, and he will give us a lecture on Hurricanes 101. For us living on a state like Delaware on the East Coast, that'll be a very important talk. So I'm going to turn it back to Rebecca, who will open the microphone so we can all thank Sandrine for a fabulous talk.
Yes, if folks would like to unmute themselves and applaud and say thank you, feel free to do that now.
Thank you.
Thank you so much.
Thank you. Thank you very much.
Thank you.
Thank you.
Appreciate it.
Thank you.
Thank you.
Merci.
Thank you.
All right. Thank you. So thank you everyone who joined us.